Hello, this is CS 471 571 operating systems, and the point of this video is to talk about making system calls in XV6 so that you'll be ready for the next batch of homework assignments. Alright, so I'm going to go straight to my program and show you, if we want to make a new system call, what we need to do. This is the list of system calls that are given to us. And remember, a system call is the part of the operating system that's running for you. So anything that we want the operating system to do for us, if it's not already in this list, then we're probably going to need to make a new system call if we want our user programs to be able to do it. I have an example that we'll look at. Alright, first of all, let's take a look. And there's two things to look at here. One is we can look at my example of a system call that does something different. And the other one is, if you were a regular person and you just wanted to figure out how to make a new system call, what would you do in XV6? So you would go and look for one of these system calls that already exists, let's say pipe, or yeah, and go and look in the code about how is pipe done. So I will, let's see, we'll take some notes under XV6. So making a new system call. All right, and we'll see what we do. First of all, let's look and see what I have. We have the primes program, which was our first program, I think. There's some other programs that I've added. One that I want to look at here is my usage. Okay, so this says that it's running a system call, and this is a printout of the data structure that's keeping track of the process that's running. So if I look at my usage.c, so here we have running my system call. It calls something called usage, and then it also prints the memory size. There's the memory size right there. The rest of this was actually printed out of the usage function. So then I need to go and look where the usage function comes from. That's actually a system call, and so we'll see in a second how that works. Just to be so making a new user utility, which is something we've covered in other videos, but let's put some notes here. So the way we've been doing it is create a new file, new utility.c with your program, edit the make file to include new utility.c where. So we could look for anywhere there was primes. So this is included in the extra variable. And new utility in the uprogs variable. And the way that I figured that out is I looked for one of their utilities to see what was in the make file for that. All right, so here's my program, and then I need to track down usage. So my method for doing that is looking for usage, and let's start with star.c. I'm in xv6, I need to close xv6. Okay, so these are not necessarily calls to my function usage, so there's a comments, there's my usage.c, and then we get to these ones. Let's see, syscall.c, that looks like something to do with my system call. Sysproc.c as well. So then I can go and check these out. All right, those are in .c files. Should also check .h. Okay, so there's .h, and we see one that is sys usage. And we see one here, which is usage. You also need to check star.s files, which are assembly. An operating system is typically going to have a small amount of code that's written as assembly, and in our project here, these are .S files, and there's one there where we have usage. All right, so now your procedure, let's say we want to make a new system call, my syscall. These are the things, so you need to do basically just the same as whatever I have for usage. So in usys.s, we need to have a syscall, my syscall, and let's see what that looks like. I put mine right at the end there. All right, and what does this do? It's a macro that puts some assembly code into this file. So each system call has an address there in this code, and then if when you actually do the system call, it's doing an interrupt instruction. So this is the instruction that goes into the operating system. All right, we don't need to know the details of how that works right now. We just do the same thing as we did for other ones. So let's see, we add a new line to the end of the file. Okay, so that's good enough for the .s. Then we want to go and look at the .h's. So in syscall.h, so we can put a new line at the end. Pound define sys my sys call, and then whatever the next number is, depending on how many system calls you may have added already. Okay, that's syscall.h. These are all here. Then we need to go into user.h. So in user.h, we have just the function prototype for how this is actually going to be used in the user programs. So whatever the parameters are and whatever the return value is going to be. My usage function, I decided it was going to have this, and return value of an int. Okay, This stuff with struct proc usage is specific to the fact that I am defining a new type there as well. So that's not necessarily needed for doing a new system call. All right, and then we want to look into the .c files, the key files to look at. syscall.c. So at the top of the file, there is function prototypes for versions of the function where you have sys on the front. And extern means those are not in this file, they're in another file. So we have that line. This is in syscall.c. Add extern int sys my syscall void line. So we do that, and we're also going to add the next, so where we see this, and this actually needs to be in the right order. Since I put, if we put the next number here, we need to make sure to put this on the end of the system call list. So we add sys my syscall with the sys there, add this line, right? All right. So that is it for syscall.c. Then somewhere, so in some file, define the sys my syscall function. It could be in sysproc.c, it could be in, that's where mine is because that's where I put it, or it could be some other. It has to be defined somewhere. All right, so let's look at mine. Okay, so then this is my function for doing usage. Let's go ahead and trace all the way through from my C program, my user program. All right, so here's my user program. I have the function usage. The reason my program knows about this function is because it's declared in one of these files, in particular in user.h. Okay, so in user.h, there's a prototype for a function, so there should be this function. It should exist somewhere. All right, and where is that function defined? So why don't you pause, look through my notes here. Where is that usage function actually defined? Where's the code for it? Okay, now it's got to be one of these options. And the right one is this usys.s. So right here, this syscall usage means that this is going to be run where instead of name, we have usage. So there's a global usage, there's a label usage, and then we move into, let's see, we do a move with EAX, and usage is the name, and then there's a system call there, this interrupt. Okay, that's the only place in my list here that we actually have something that's just usage. So that has to be the one that actually gets run. And you see it has this sys underscore business. And so that's tied in with this stuff in syscall.h and syscall.c. So if we look in syscall.h, there's a number. So this sys usage is system call number 22, and then that gets tied in with syscall.c. So there's this array here of system call functions and numbers. So this is number 22, and this is the function. Okay, so what happens is when I have usage in my program, what's going to happen is 22 gets put into the CPU here, and then we call the system call. We do the interrupt for the system call. All right, and the interrupt handler for the operating system must have been set up so that it's going to take that number, this number. It must have been set up so that it's going to take this number and look it up in this table. So this table has to be in there somewhere, so that when the code for this interrupt, that it's going to look up in the table for that function. And so then this function right here is the one that starts running, and I have that defined somewhere here. All right, and all of these functions are void arguments and return integers. And if they actually have arguments or return values, that's handled somehow. All right, so for your first system call, you would get all this stuff set up, and then you could do a cprintf, which prints to the console, and you could print hello world just to make sure that you're actually getting to that code. All right, what I have here is I want my system call to take a pointer, and they have a function called argpointer that we can use to get the that pointer safely. Let's see. So this is a concept that we can keep note of somewhere. Let's see. When writing operating system code, we want to be careful not to let bad user processes let's see, if there's bad user processes, then we don't want to break the system. Right, if we're the operating system, then we need to make sure that whatever see here, I'm in the operating system now. When you're in the operating system, then we're allowed to do everything. We can control everything, and we need to be paranoid about checking parameters and things like that. So we must check parameters thoroughly, paranoidly. And that's what this function is here for. There's the variable that's going to get the pointer. So I have a local pointer here. I'm in the kernel. That's in kernel memory somewhere. And so I give the address of that. This 0 means that it's supposed to be the 0th argument that the function gave me. If the function gave me more than one argument, then this would be 0, 1 or whatever. And then this says how much memory does this pointer have. It's typecast to a char star, so I have address of u because it's going to put this pointer into u. If it's going to put something into u, I need address of u. U is a pointer. Char star, it works. You can typecast pointers to anything. If it's just setting a pointer, that's okay. And then an extra star because I'm taking the address of that. Okay, so I tell argpointer, 0th parameter, please put the pointer here. This is how much memory is supposed to be there. And what it's going to check is that the address, this pointer that it's giving us, is actually okay. It's not trying to be sneaky. If we look at our picture of memory, this one here. All right, so this is what things look like to a user, and it should be giving us pointers from user space. If it tries to give us a pointer up here with a kernel address, that's not okay. What it's supposed to be given here, right? So what my program did here is it gave me address of where to put. It's going to put some information, and this is where to put it. Okay, and since this is running in user mode, it's a regular program, this variable is going to be sitting in the user stack. It's a local variable. It's sitting down here, so the address for that is going to be down here and not up here. Argpointer is going to check that address to make sure it looks all right. And if you want to, you can go look up argpointer in the code. So you'll see syscall.c actually has that defined, and then it gets used. Those are system calls that use argpointer. All right. If the argpointer function sees a problem, it returns -1. It returns less than 0. Right, according to my check here, and then we bail out. If I get past there, then this was an OK pointer. It points into the user memory somewhere, and then I can go ahead and run with it and use it and put stuff in there. Note the program could have given me a bad address in here. If I'm the operating system, I'm not so concerned if the program messes itself up. That's okay. So I would just use it. And that would be like having a buffer overflow or something in your program. The operating system is maybe going to let you do that until it causes some other problem. Okay, so in my usage system call down here, what I'm doing for this one is I wanted to look at all the process state that the operating system keeps track of. So inside the operating system, there's a list of processes. And in proc.h, there's a struct here, struct proc, and this is information that the x86 is keeping track of for each process. So it's the how much memory has been allocated to that process, information about virtual memory for that process, which we'll talk about in an upcoming video. Another thing about memory is the process running or waiting on a file or something. So state there says whether it's running or waiting for something or runnable. The process ID that's unique, 0, 1, 2, 3, and so on. Information about the parent process. In my program, I say my usage, and what is the parent of the my usage program? It's what process created the my usage process. And there, the parent is the shell itself. And this address here is where in kernel memory that struct proc is. And then inside of that struct proc, I can look at the name. I have the name of myself. That's printed here, my usage. That's the name of myself. If I go into the struct proc for my parent, I could look at the name of that. This is about the handling of the system call itself, information about the CPU, so the whole contents of the CPU, all the registers and everything. When a process gets switched out, then you have to save the entire state of the CPU, or at least the parts of the CPU that you're going to use again. So that's there. Then we have a list of open files. So these would be list of open files, and then the current working directory of the process. All right, so that's information. We don't know what all of that stuff means, but I just wanted to practice writing a system call by printing it all out. And we can look at my program here, and if 1, that means true. So do proc dump, and I just put that up here in a function. So there's a function that we can call myproc that gives the struct proc pointer for the currently running process, whatever process is running the code right now. And then I have these cprintfs. I basically just get the process struct proc pointer and then print everything in there. For the parent, it's a pointer to a struct proc, so I went ahead and, as long as it's not a null pointer, I print the pointer and the name. Same thing with the current working directory. I looked up for the current working directory is a struct inode. If you look that up, struct inode has a device and an I number. I went ahead and printed those out as well. That may mean something to you or not. All right, so that is how to make a system call. What you should do is, pause and think about what are the different things that you have to do to make a new system call, just to get started, just to get hello world. All right, pause. All right, so now we have that information here. This is where you want to go. And if you don't, how to do something with files or memory or the CPU, generally speaking, find the existing xv6 system call that is most similar to what you want to do. Right, so if I want to do something with, for example, let's just say I want to make a system call that gets system info, which includes how much memory for all user processes and the total number of processes and the total number of CPUs. Let's just say we wanted to do that for some reason. Then you would look through the system calls and pick out the ones that do something similar and look at the code for those. Okay, I think that'll be it for this one. We'll do another video talking about the homework assignments sometime soon.